All right, let's talk about how we graph x, v, and a graphs. We know that they're all functions of time, and I want to show you how they're all related. Remember the kinematic equations of motion. In this discussion, I'm going to talk about these equations and show how they're related to each other and how the graphs of x, v, and a, all versus t, will always look. They're always going to look the same way. At the heart of our kinematics equations is the assumption that our acceleration is constant. That means we're always going to deal with an acceleration that is either positive, negative, or zero and never ever changes. So let's start with x versus t graphs. Remember, x is the variable that describes where or how far. It'll tell us where in our number line our object is. Here's the important kinematic equation for x. Remember, x will be a function of t. You should have talked about that in your math classes, so you should be fairly familiar with functional values. We have some constants in the problem. We have the initial x position and the initial velocity and then the acceleration. So here's the equation. xf of t is equal to x initial plus vit plus 1/2 at squared. Look at that equation. You should from math recognize that this is a quadratic equation, and that means it's going to be a parabola. Parabolas are curvy. So anytime you see an x versus t graph that is curvy, it means you have a non-zero acceleration. Here's an x versus t graph that is curvy. Let's take a look at that. It seems to show that the distance each second is getting larger and larger. It's increasing more and more. That would indicate a positive acceleration, so you are speeding up. Here's another x versus t graph that's curvy, but it appears in this case that the distance in each subsequent second is getting less and less. You're still moving forward, but you're covering less and less ground. This would be an indication of a negative acceleration. Still moving forward, but slowing down. Here's what the graph looks like. Finally, here's the third type of x versus t graph. In this particular case, there's no curviness in the graph. This would indicate that you have a zero acceleration. If you look back at the original kinematic equation, it reduces down now to x final of t is equal to x sub I plus vt. This is the equation of a line. A linear x versus t graph immediately tells you that there is no acceleration. Now let's look at v versus t graphs. Here's the kinematic equation for velocity. Not too bad, v final of t is equal to v initial plus at. This is also a line with your y-intercept v initial and your slope a. Here's some graphs of constant velocities. This shows all three classes. You will never, ever, ever see a v versus t graph look like anything else. It is always going to be a line. It's always going to be sloped down, sloped up, or flat. Again, this is the equation of a line. It's either sloped up for a positive acceleration, it's sloped down for a negative acceleration, or it's flat, indicating zero acceleration. Now, finally, let's look at a versus t graphs. These are the easiest of the graphs. We actually do not have a kinematic equation for it. It's just a constant. If we were to write such an equation, it would look like this. A as a function of t is a constant. That means it never changes. It always stays the same value. It's going to be a positive constant value. That means you're speeding up in the x direction or the positive direction, or slowing down in the negative direction. You can have a constant negative value. That's slowing down in the positive direction or speeding up in the negative direction, or a constant zero value, meaning you're not speeding up or slowing down at all. This graph is just going to be straight lines. So to the right shows you what the graph looks like. It's always, always going to be flat lines. The blue line is a positive acceleration. The orange line is a negative acceleration. The black line is a zero acceleration. So let's look at the relationships between the graph. Remember this little thing I showed you before. If you have an x versus t graph, the slope gives you velocity. And then if you have a v versus t graph, the slope gives you acceleration. You should be able to look at an x versus t graph and either estimate or draw a v versus t graph. Remember that the slope of x versus t is the velocity. Similarly, after you have the v versus t graph, you should be able to look at it and estimate or draw an a versus t graph. Remember, the slope of v versus t is the acceleration. Let's see how this works. So here's a graph of position versus time. Notice that there seems to be three regions in the graph. I have something happening between 0 and 2 seconds, and then from 2 to 4 seconds, and then from 4 to 9 seconds. If I had to tell you what was happening here, it looks like I start at the origin. I am walking forward for the first 2 seconds. I am then standing still for the next 2 seconds, and then I'm walking backwards for the next 5 seconds. You should be able to easily draw a v versus t graph. The slope of the x versus t line in the top graph between 0 and 2 seconds is constant positive. That means the velocity is positive and constant between 0 and 2 seconds. The slope of the x versus t graph between 2 and 4 seconds, the slope of the graph between 2 and 4 seconds seems to be 0. And so that would indicate that you have 0 velocity. Finally, the slope of the x versus t graph between 4 and 9 seconds is negative and constant. That would indicate that the velocity between 4 to 9 seconds is negative and constant. How do you graph constant values? You graph them as flat lines. So the v versus t graph would look as follows. Between 0 and 2 seconds, I have a constant value. Since I gave you numbers in the upper graph, you could actually tell me what the slope is. Between 2 and 4 seconds, the slope is 0. That is a 0 line. And then between 4 and 9 seconds, since I gave you numbers, you could actually calculate what the value is. If I give you numbers in the graphs, you should calculate slopes. If I don't give you numbers, you just estimate them and show what they look like. Here's an acceleration versus time graph. Wow, look at that. All the regions of the v versus t graph are flat. That means the slopes are all 0. That means the acceleration is 0. No curviness in the x versus t graph, no acceleration. Be aware that the graphs on the previous slide are impossible. You cannot instantaneously change your direction or change your velocity from some value to 0 or negative. Doing so would cause really bad things to happen to you. You would break bones or hurt yourself really badly, or objects would deform immeasurably. Think about running into a wall at full speed. You have a constant positive velocity, then you hit the wall, and then you have a 0 velocity. If that happens in real short time, you'd hurt yourself really, really bad. So, anyway, you should see how easy it is to derive a v versus t from an x versus t, and then an a versus t from a v versus t. It's a little harder when the x versus t graph is curvy. That's going to be the next few slides. Let's consider an x versus t graph with acceleration. So here's what it looks like. It's the one we saw before. It had some curves to it. Remember how you find the slope at a particular point. We pretend like the curve is part of a big circle, and we find the tangent line at that particular point. If you find the slope of the tangent line, that would be the velocity. So let's look at tangent lines at t equals 10 seconds and t equals 20 seconds. Here's the line at 10 seconds. I've tried to draw the red line, so it is just about tangent at 10 seconds. And here's the one at 20 seconds. Again, I've drawn it to try to be tangent at the point at 20 seconds. Notice that the slopes of the two lines are different. Without any numbers, it looks like the slope of the line at 10 seconds is smaller than the slope of the line at 20 seconds. This would seem to indicate that the slope is increasing as time increases. Slope is velocity, so this would indicate that the velocity is increasing. We actually know how it has to increase. The velocity versus time equation is a linear equation, so the graph of v versus t has to be a linear value. Finally, if I took the slope of the v versus t graph, I would get the acceleration. Looking at my v versus t graph, it looks like I have a constant positive slope. That means my acceleration is a constant positive value. How about x versus t with a negative acceleration? This would be a situation where you're slowing down. So here's my graph now. It looks like a parabola that's opening to the right. I want to look at the tangent lines again. We'll pick 10 and 20 again just because they're easy. There's my tangent at 10, and there is my tangent at 20. Again, without any numbers, it seems clear that the slope at the 10 seconds is larger than the slope at 20 seconds. That seems to indicate that my slope is decreasing as time increases. Slope is velocity, so the velocity is decreasing. It's still positive. We're still moving forward. We're just moving forward slower and slower. Here's what a velocity versus time graph would look like. Again, we know how it has to decrease. V versus t is always a linear function, and so the graph is always going to be a line. Since my velocity is decreasing, it decreases in a linear way. Finally, the graph of the slope of the v versus t graph is the acceleration. The slope of my line seems to be constant and negative, meaning my acceleration would be a constant negative value. That's it for making v versus t and an a versus t graphs given an x versus t. Don't think too hard about this, but mathematically, you're doing calculus. Anytime you hear the word slope or tangent, you're really taking the derivative of a function. I think that's very cool, even though you don't know that you're doing calculus. We'll talk about going the other way in another video. In other words, we'll start with a constant acceleration versus time graph, and then we should be able to work our way backwards and determine a v versus t and an x versus t graph. This is also calculus. This time, it's called integral calculus.